Okay, so I've been talking about the inner workings and the characteristics of OSPF. I've mentioned the link state database, and link state updates. A link state update essentially contains one or more LSAs. These LSAs contain information about routes to given networks. Like I said, they usually initially send type 2 DVDs, a list of routers in the LSTB. The routers look at their own lists and realize and compare to determine, hey, is my neighbor talking to me about a router I don't already know about? And if the answer to that question is yes, um, the type 3 LSR, the link state request, goes out from the router which just received new interesting information to the router which advertised that new interesting information. Um, and the router which initially sent the DBD now builds a link state update containing these LSAs, link state announcements. So, and of course, our type 5 acknowledges the other packet types. There are a number of different LSAs, and this is another this is another sort of table that you should probably put in your notes, or otherwise commit to memory. Um, Type 1 is a router LSA. Type 2 is a network LSA. Type 2 LSAs are only relevant if you have to have a DR or a BDR election. Um, 3 or 4, those are summaries, as in a summarization, a list of networks summarized in a network aggregate, or what we would call a supernet. Um, a type 5 indicates an LSA that is external to the autonomous system. Essentially, it advertises an ASBR. And the ASBR, of course, probably has a default route off the autonomous system. Then there's type 6, type 7, type 8 would be for a BGP router that's interacting with your OSPF routing domain, and 9, 10, and 11 are what we call opaque. We will come back to this table. We will use parts of this um, in more detail. So let's talk about the states. Just like um, other kinds of protocols that we've used in the past, say, for example, spanning tree, um, it moves through various operational states, and you can tell what your network is doing or where it stopped working by what state it's in. So let's look at that for a minute. So our operational states. Everything starts, our first step is to, let me move myself again, hide the Cisco logo, I guess. Okay, that's fine. Yeah, yeah, this is, okay. So the first step, the first phase, shall we say. So there's steps, and these steps happen in phases. The first phase, everything starts off in the down state. The router is capable of OSPF routing. It has an OSPF routing process, but it hasn't received any hello packets from any other router. So it starts sending out hello packets. In the init state, um, the routers have started exchanging those hello packets, telling each other about their router IDs and such. In the two-way state, routers which are on an Ethernet link are in the process of electing a DR and a BDR. And it is okay for them to get stuck in the to be stuck in the two-way state for a little while. So the first three states are down, init, and two-way. And two-way, however, only happens if it is a DR BDR situation. In the next phase, after those neighbor adjacencies have formed, they begin to synchronize their databases. So we've gone from establishing the neighbor adjacencies to converging the network, synchronizing the database, creating the LSDB. Remember, by definition, in OSPF, the network is converged when there is a link state database, when all of the routers have the same link state database. They will have their own SPF tree, their own neighbor table. They will all have the same LSDB. So in the X start state, they are negotiating their relationships. They are sending out, the master sends out the DBD Then they go into the exchange states. So XStart is exchange start. In the exchange state, the routers are exchanging their DBDs. If they need additional information, they go into the loading state. In the loading state, they are using LSRs and LSUs and LSAs to go back and forth and update each other on the shape of the lay of the land, the shape of the network. And then in the loading state, once they all have the same LSDB, they take that LSDB, they push it through the shortest path first. Each router generates its own SPF tree for the database, for the topology, and then they transition to the full state. They have converged databases, and they have routes that they can now install into the routing table. So step one is to establish our neighbor adjacencies. So we were in the down state. When they go to the init state, they start announcing themselves. My router ID is so-and-so. Is there anybody else there? That goes out multicast. In the init state, the neighboring router receives a hello packet. It sends its own hello packet. The reply goes back unicast. So some of this is working multicast to all possible OSPF routers, and some of it is going back unicast, sort of the bounded triggered update thing. It's a dynamic that you would see with EIGRP. So if they realize that they are on, in this case, for example, we've got R1 and R2 on a common Ethernet link. When they notice, hey, this is an Ethernet network, even if it is a /30, and there's only one other router on that line, they are still going to do a DR-BDR election. So they're going to elect on the basis of priority and router ID and so forth. One of them will be the DR, the designated router. One of the other will be the BDR, the backup designated router. Now, that becomes important because once the routers in that multi-access network know who the DR is, all of them establish neighbor adjacency with it. Now, if it drops off the network, they will then reestablish neighbor adjacency with the BDR rather. We'll get into and let's look at that in a little bit more detail right now. So, as I said, we have this, and I got to move this again. I'm all over the map. We need to build DR-BDR relationships in a multi-access network because of the math of full meshes. For n routers, there are n times n-1 over 2 possible adjacencies. So with 3 routers, there are 3 adjacencies. With 4 routers, there are 6 adjacencies. With 5 routers, there are 10 adjacencies. With 20 routers, there are 190 of them. Now, that's a lot of LSAs bouncing around back and forth. That's a lot of overhead on the network and a lot of unnecessary, frankly, topology computation. So instead, what they do is they all relate to one guy. Say, for example, let's say this one down here, on the bottom. Let's say this guy is our DR at the end of this process. All of them establish neighbor adjacencies with him. So that's 5 neighbor adjacencies, not 10. Or 10 neighbor adjacencies, not 45. So this reduces the number of neighbor adjacencies, the number of LSAs bouncing around, etc. It speeds the whole thing up a lot. So let's talk about database synchronization. So now this is only going to happen in an Ethernet network. If you build your OSPF topology using a non-multi-access technology, say serial lines, never even happens. So after we get into the two-way state, the routers have to synchronize all their databases. And I got to move me again. Now I'm over here. Router, they'll get into the exchange, the XStart state, step 1, the XStart state. They'll go into the exchange state. and they'll start bouncing LSDB information back and forth. They'll summarize it with a DBD. When they look at their own information and the information that they've received in that DBD, they'll compare. It's kind of like comparing the configuration revision number in a VTP packet. The switch receives a new VTP packet, it looks at its own configuration revision number, it looks at the configuration revision number in the packet it just received, in the VTP frame it just received, and it realizes, wait a minute, you're on my domain and you have newer information than I have. Please tell me what you have. On a good day, that means you change the name of a VLAN, or you drop a VLAN that you're not using anymore, or you rename a VLAN to nothing. On a bad day, if you have a if you have a new switch which added to the network without being properly sanitized first, you can poison your VTP. But that's not happening here. But it's the same idea. They're looking at their own current information plus the information about the information that they just received. So from a certain point of view, these DBDs and even these configuration revision numbers in VTP, you can think of this as metadata, data about data. So they receive this information, they bounce it back and forth, and at the end of it, they get to they all end up with the same database, with the same link state database, and then they can crunch that through the SPF tree. Now, the next thing in Netacad is actually a video. So what I suggest you do, if you've got Netacad, is go watch that video. I think it's let's see, I think it's 8.1.3.6 in the current Netacad version 6. Go watch that, because frankly, if we were in class, I would be playing it right now. But I can't very well play a video of a video. That will be silly and a violation of copyright. So the next thing on our to-do list is single area OSPF v2. So that's actually kind of going to be a different, a slightly different video series. I'll get to that soon. Thank you for watching.